Hi everyone, welcome back to part 2 of the lecture on chain rule. What we're going to do is we're going to pick it up with this idea of implicit partial differentiation. So what I want you to do is I just want you to think, as we're going through this in its general form, you can think of a particular example. Think of a sphere, which has an equation x squared plus y squared plus z squared is equal to 1. And think about how we would find the partial derivatives, dz dx and dz dy. So think about how we would find those. So we'll do that in this box up here, which says implicit partial differentiation, but we'll go through the details. But it's good to have a concrete example in mind, and so you can think about the sphere in this case. So the main setup is we've got a surface which is defined by an equation, and what we'll do is we'll just rewrite this equation of our surface as everything involving x, y's, and z's and all the constants on the left hand side, and we'll just make it 0 on the right hand side. Now that we've got an expression involving x, y's, and z's, we can think of that as a function. So that's where we're starting with. We're starting with a function of x, y, and z. So if you want to think about our sphere case, I will just get rid of that equal sign, make it a -1, put it equal to 0. And so in this case, that is like our f of x, y, z function in this concrete example. So now in order to find the partial derivatives of z with respect to x and z with respect to y, this statement says that you can find those by taking that big function, capital F, and you can take its x partial and divide by its z partial and put a negative sign in front. Or to find dz dy, you take the y partial of capital F and divide by its z partial and stick a negative sign in front. And so the question really is why? Why can we get these partial derivatives dz dx, dz dy in this way? Let's see why that's the case. So we're going to start with our equation for our surface. F of x, y, z is equal to 0. And step 1, we will just differentiate by x, or differentiate with respect to x. Maybe I'll say with respect to x. And I'll say both sides. So differentiate both sides with respect to x. So when I differentiate the left-hand side, thinking differentiating with respect to x, but it's a function of 3 variables, x, y, which is independent of x, and z, which is a function of x. So I need to use the chain rule. Derive the outside function with respect to x, multiply by the derivative of the inside with respect to x, so dx dx, plus df dy, dy dx, plus df dz, dz dx. And that's equal to the derivative of the right-hand side, which is 0. And of course, the main idea here is that dx dx is 1, dy dx is 0, and dz dx, this is what we want to find. So want to find. This is the thing we're interested in. Because if you think about the question when we were talking about the sphere, dz dx, dz dy were the partials we wanted to find. So how do we find it? Well, this is now just an equation. So I'll simplify it just a little bit. I'll write df dx as just f sub x, that's times dx dx, which is 1, plus df dy times 0, plus df dz times dz dx, that's equal to 0, or in other words, dz dx is equal to negative the x partial over the z partial. And that's the equation that we were hoping to derive. So that verifies that first equation in the implicit partial differentiation box above. We can do the same thing, differentiate both sides with respect to y, and a similar calculation or similar computation gives that dz dy is equal to negative f sub y, or the y partial, over the z partial. Alright, so that's impartial differentiation. We can think of it in terms of that sort of big function involving x's and y's and z's. And then we can work out the corresponding partial derivatives of z with respect to x and y using the partial derivatives of that big function, capital F. Let's look at an example of how we're actually going to use this. So there's going to be two problems. This is problem A. So let z be a function of x and y, and we assume that it satisfies this equation. So this equation is going to define a surface. And we can get a visual for what this surface is. It's not necessary to solve this problem, but we can get a visual. So there's our surface. And that red point that's plotted there, that's the point that we're interested in finding our linearization at, as the part 1 of the question is asking us to do. So we'd like to find our linearization at that point. Now in the question it says you're interested in doing things at the point 2, 4, 1. And the reason it's giving you a z value of 1 in the question is because that point that we're interested in is 2, 4, 1, but there's also another point, 2, 4, 0, and another point, 2, 4, negative 1. Those all live on the surface with x coordinate 2 and y coordinate 4. In fact, if I just look at the vertical line that passes through 2, 4 in the xy plane, then it intersects our surface in those 3 points. So just knowing the x coordinate and the y coordinate of a point for a surface given by an equation is not enough. We may need to specify its z coordinate because there could be multiple points that have the same x and y coordinates. So maybe that's the first thing we should do, is say, what happens when x equals 2 and y equals 4? How do we know there's those 3 points? Well, when we plug those in, we get a z cubed minus z plus 2 times x times y, that's 16, minus y squared, that's also 16, so that's 0. So z cubed minus z is equal to 0. Or in other words, z is equal to, the solutions to z cubed minus z equals 0, there's 3 of them, plus or minus 1 and 0. And we're interested in the point that has corresponding z value 1. What would we like to do with that? Well, we want to find the linear approximation at that point 2, 4 with z value of 1. So let's write down, what is it we're trying to find? We're trying to find the linear approximation. So we need to know the z coordinate of the point in question plus the x partial of that point times x minus the x coordinate of the point we're at plus the y partial at that point times y minus the y coordinate of the point we're at. And so that's what we're interested in finding. To find these partial derivatives, dz dx, dz dy, we use this big function, capital F of x, y, z is equal to, and I look at the equation of my surface, and I pick off the left-hand side, the side, well, as long as I've set the left-hand side equal to 0, then I'm picking off that left-hand side. In this case, it's of the right form. It's this thing equal to 0. So there is our function we're interested in. dz dx, that's given by negative f sub x over f sub z. So the negative the x partial, which is 2y, all over the z partial, which is 3z squared minus 1. And in particular, we want to know that z partial, or sorry, that x partial at the point 2, 4, 1. And so we can plug 2, 4, and 1 in, and we get negative 2 times 4, so that's negative 8 up top. And then 3 times 1 minus 1 is 2 on the bottom, so negative 4. So there's our first derivative we're interested in, our first partial. And then the other partial derivative we want is the y partial, so that's negative f sub y over f sub z. The derivative with respect to y, so it's negative, and then it's 2x minus 2y, and all of that's over the z partial. In particular, we're interested in the case of the partial derivative at 2, 4, 1. And so that would be 2 goes in for x and 4, so that would be 2 times x is 4 minus 8. So that's negative 4, but there's an extra negative, so that's a 4. And the bottom's still 2, so that has a value of 2. So notice it was at that point, maybe I'll change the color, it was at that point, that's where we used the value of 1 for our z value. If we're interested in any of the other points on that surface and the partial derivatives there, well, we would use the different z value corresponding to the point. So that's where we use the 1. And so now this means we can write down our linearization. L of xy is equal to, so I'm just using that expression up here, that's 1 plus negative 4 x minus 2 plus 2 times y minus 4. And so there is our linearization. Now I'm going to want to go ahead and just plot this to get a visual. So I will rewrite it in a simpler form. But the idea is I want to use the form that I've just written down in the next question because I'm asked to estimate the value at a nearby point. So I'd like to have it as x minus 2 and y minus 4 in my expression. But if I'm going to plot this thing, it might be better to have it cleaned up a little bit. So to clean it up, I'll just jot a few things down here. That would be negative 4x plus 8, and that's plus 2y minus 8, and that's a 1 plus. So we would get those 8's canceling, and that would be a 1 minus 4x plus 2y. There's our nice simplified expression. So if I go back to our demo, and I'm interested in what's going on at that red point and plotting the plane, so I'll get rid of those other points in the line, and I'll plot that plane that I just constructed the equation for, the function that defines the plane, the linearization, 1 minus 4x plus 2y. When we plot it, that gives us the tangent plane to the surface at that point. And I can use that tangent plane to approximate other nearby points on the surface. So that's what we're going to do in the next part of this question. Use our answer in part A to estimate the value at that nearby point. So I'm just going to get rid of this, and we'll go ahead and we'll work on part 2 now. Use our answer to estimate the value. So I will write it down like this. F of 2.02 comma 3.96. Actually, I don't think I had a little f defined anywhere, so it doesn't make sense to introduce it now. I will say then instead, because we've just been using z, the z value corresponding to those xy values. That's approximately given by the linearization, 2.02, 3.96. And that is 1 plus negative 4, 2.02 minus 2, that's 0.02, sorry, 0.02. That's why I like to leave it in the x minus 2 form and y minus 4, because the next one, 2, and then y minus 4, that's 3.96 minus 4, so that's negative 0.04. And so there is our corresponding values plugged into the linearization, and we can work out this. This is roughly 0.84. And so what we have is that the z value is approximately given by 0.84. So that we use the points on the tangent plane to approximate the points on the surface, because the tangent plane is a good approximation of the surface near the point in question. All right, let's have a look at another example. This is the second example, or the second problem. So in this next example, we have x and y are both functions of u and v, as shown by these two equations. But we're going to think about u and v as implicitly defined functions in terms of x and y near these points in question, xy equals 2, 0, uv equals 1, 1. And because we're thinking of u and v as functions of x and y, we can ask for their partial derivatives. So for example, what is the partial derivative of u with respect to y? Well, the key thing is we only have these two equations to work with. So what we're going to do is we're just going to take that equation. I'll leave a little bit of space because I'm going to do something to these two things. I'm going to take that equation and I'm going to differentiate through with respect to, well, what variable do I want to differentiate with respect to? Well, I'm ultimately interested in the derivative with respect to y. So that's the derivative I'm going to take, the derivative with respect to y. And when I do that, the derivative of x with respect to y, that's 0, because x and y are independent. And then for the next piece, I'm differentiating through this function of u and v with respect to y, because I'm thinking of both u and v as functions of x's and y's. So this is a perfect opportunity to apply the chain rule we've just been developing. And so that means to differentiate this expression involving u's and v's in terms of y, I first differentiate it with respect to u, that gives me a value of v, times du dy, plus the derivative of that expression with respect to v, that's u plus 2v, times dv dy. And then we can go ahead and do the next equation. The next equation is y is equal to u squared minus uv. I want to calculate its derivative with respect to y. And so the derivative of y with respect to y, that's 1. And then this derivative, we use the chain rule again. It's derivative with respect to u, that's 2u minus v times du dy, plus the derivative with respect to v, that's negative u times dv dy. So now what do I have? I have two linear equations in the derivatives du dy and dv dy. So I have two equations, two linear equations in two unknowns, the things I'm trying to find. And so this is a perfect opportunity to apply techniques from linear algebra, for example, solving two equations for two unknowns. You can set up a matrix, etc., etc., and go ahead and try to solve these things. But the way we're going to do this is we're just going to isolate one of the variables. So we'll go ahead and we will solve for dv dy in the first equation, and I'll solve for dv dy in the second equation. You may say, why did I choose to solve for dv dy? Well, I'm interested in finding du dy. And so I'm going to isolate for dv dy, and you'll see why in a second. So dv dy, I can push the negative v to one side, divide by the u plus 2v, and that gives me a du dy. So that's the first equation solved for dv dy. The second equation we get, so I have a 1 minus 2u minus v du dy all over a negative u. So I'll put a negative u there, and then I'll change that to a plus and then move the u underneath there. And so there are the two equations we get by solving for dv dy. The main idea here is that these have to be equal. And so what we get is that these equations are equal. So plug in uv equals 1, 1 and solve for du dy. So that's our next step. So I'm going to take this first equation and I'm going to plug in 1, 1 into it. So I get a negative v, which is 1, all over u plus 2v. So that's a negative 1/3 du dy is equal to, it's got to equal this equation with 1, 1 plugged in to it. So that's negative 1 plus 2u minus v is 1 over 1. So that's du dy. And so there's our equation in du dy. And so that tells me then that I can move the negative 1/3 du dy over to the other side. That gives me a 4/3 du dy is equal to 1. Or in other words, du dy is equal to 3/4. So we've managed to find the derivative we are interested in. And even though it wasn't asked for, we could find the other derivative. Also, dv dy, what would it be? Well, dv dy is going to be given by either one of these two equations. We got this equation or this equation. And so maybe I'll take the first equation. dv dy is equal to negative v over u plus 2v, so that's negative 1/3 du dy. So that's 3/4, or in other words, negative 1/4. So that's dv dy. And now we can go ahead and answer the second question. If z is equal to u squared v cubed, compute the derivative of z with respect to y at the point in question. So z is u squared v cubed. And so the partial derivative of z with respect to, let's double check, what are we differentiating with respect to? With respect to y at the point xy equals 2, 0. So the derivative with respect to y, so it's the derivative of this with respect to u, which is 2uv cubed du dy, plus the derivative of z with respect to v, it's 3u squared v squared, times dv dy. And we're interested in at precisely the point when xy equals 2, 0, or uv equals 1, 1. So that's the point in question. So let's go ahead and pop those things in. That'll be 2. du dy, we worked that out above. That's 3/4 plus 3 times u squared times v squared times dv dy. We worked that out above. That was negative 1/4. And so this becomes 3/2 minus 3/4, or 6 minus 3/4, or in other words, 3/4. So there's our partial derivative of z with respect to y. So you notice there's a few things that were going on here because of the fact that x's and y's were functions of u's and v's, but we were thinking of the reverse relationship that u and v are actually implicit functions of x and y, that when we did the derivatives we got a system of linear equations. And that's not a surprise here, because the idea with derivatives, differentiation, calculus in general, is to take curvy things and make them straight, or to take nonlinear things and to approximate them by linear things. And so what we've done here in taking our derivatives, if we've taken expressions for x's and y's that are mixed up involving the u's and v's, and we've extracted from that, using the derivative, some linear relationship between their derivatives. And we then used techniques for solving linear equations to solve for those derivatives. And so this is how these ideas can get used. Things that aren't linear, using derivatives, we can produce linear things and use techniques from linear algebra. If they were more complicated than this, we may have needed more techniques from linear algebra, but for here it was just solving two linear equations in two unknowns. All right, so that's it for this section. Thanks very much for watching, and we'll see you again next time.